All right, hello everyone. My name is Blaze, and today I'll be taking you through some Gillespie's algorithms in Python. Now, this is a very intro video. I hope to make it a kind of sequence of a couple in a row. So first, I'll kind of outline some limitations of ordinary differential equations and compare ODEs to stochastic simulations. Then I'll use Gillespie's algorithm as an example. I guess I misspelled that. Oh, maybe not. I don't know. But anyway, Gillespie's algorithm as an example of a stochastic simulation. I'll show what it means in a flowchart, and then I'll write it out in Python or show you some code, and then do a simple little example, and I'll wrap. I hope to make it about a 10-minute video, no more, but we'll see how we go. Okay, so first of all, with ordinary differential equations, there's a couple assumptions that you need to understand that ODEs make. First of all, that the solution is dilute and well mixed. Many copies of the species are present, so species are represented by real valued concentrations. These are definitely some fallbacks, especially because some biological systems involve reaction networks with small copy numbers of species. And so being able to control the copy numbers or not being able to control the copy numbers of ODEs is in the use of ODEs is definitely a good or a big fallback. And so you can't really model well using small copy numbers, and that's really the important things. And so this brings in the idea of stochastic simulation, and essentially Wikipedia has a good little blurb and a good page on it. But this is a simulation of a system that has variables that can change stochastically randomly with individual probabilities. And so basically, these random variables, when you go through some sort of stochastic simulation, are generated and inserted into the model, and then you loop and loop and loop until you run out of time, or you get a zero propensity. That is, maybe a copy number so low, or the amount of some sort of reactant that's so low that you don't actually get any reaction. And so one person who modeled this stuff was Gillespie, and that's his name. This is kind of a flow chart of Gillespie's algorithm. So we have an initial state vector, the initial conditions we can store it as a state vector, but then once we go through another loop, it'll be saved as a new state vector, and then we'll enter the algorithm again. And we'll also want to set the current time to 0, and then at the end, we'll add time to it as we go through and through and through. So the first question we need to ask ourselves is if the total propensity equals 0. So if we calculate the propensities of the reactants and the reactions, and or the reactants based on the reaction properties, if the propensity is 0, then there's not going to be any reaction to take place, so we exit and we're done. We return what we need to return. But otherwise, we'll continue on if the propensity is positive or negative or whatever. It depends. That would depend on K, or the reaction constant that's pushed the reactions forward or backward or whatever. So the next thing we would have to do is draw a time to the next reaction from an exponential distribution with mean equals 1 over total propensity. Essentially what this is picking a random time, a very small increment of time, so that one reaction takes place. And so this 1 over total propensity will take some random time series that's really small, and say that one reaction happens in that time space. And and the pros of that is like, oh, if one reaction happens, then the whole state of the mixture or the reaction mixture changes, and so we can model one at a time, essentially. Next question we want to ask ourselves is if the current time plus the time to the next reaction is greater than the simulation length. If this is just like how long we want to simulate this for, right? If this is greater than our simulation length, we exit. But if not, we continue on. So if we pass both of our hurdles, we continue on and choose a reaction, a random reaction, based on the probabilities, and the probabilities are based on the weights, which are essentially propensities of the reactants and reactions. So then we randomly choose one of our reactions to take place. Then we will apply that chosen reaction to the state vector, because that state vector will change in our first go round. our initial state vector will change to, this new state vector. And then that state vector will be used in loops and loops and loops. And then we'll also just add and save the time so that we can then graph it and save the data later. And so we will loop, loop, loop. The only outs that we want in our algorithm are just when the propensity is 0, when we don't have any potential for reactions, or if the time runs out and we desire, or the time that we desire to model for runs out. So that's the whole idea. So I went ahead and put this into a Python model. I'll start. I use Google Colab. I've started to really like it. It has a bunch of libraries, so I don't have to install anything. Plus, I've kind of gotten addicted to TensorFlow recently, so it's been good. Anyway, first couple things we want to do is well, I want to give you an idea of well, we need to import our libraries. NumPy will plot our data at the end, so we use matplotlib, and then random. This will be used in our algorithm. But first, I wanted to show you all how this random choices method works. So if we have some population excess, let's say A, B, C, D, E, this random choices allows us to pick from a population based on some amount of weight and choose some number of objects without replacement. So basically, if I run this random choices on my population A, B, C, D, E, and weight those A, B, C, D, E's differently, if I run this random choices 1,000 times, I will get an output based on these weights. That is, A, maybe if I do it 1,000 times, I could expect 100, and for B, if I weight it twice, these are all, of course, added up to 10 to make the math easy, but we could expect it to be 200, 400, 200, 100. They're all pretty relative in this case. Anyway, that's the idea of that. So random choices we will use in our Gillespie algorithm below. And you can kind of see, just for example, if I print all of these out, A is 99, B is 188, 186, 429. They're all kind of very similar to these, right? They're random or pseudo-random, but that's a whole different conversation. So let's actually get into our Gillespie algorithm. This was redundant, but whatever. Because I already imported it, but okay. If I define this as Gillespie. Now we have n, v, y naught, t length. Now n is the stoichiometry matrix. V is the rate function v. This is based off the state of the function, and but it gives us the propensities as a function of the current state. Well, that's a better way to say it. And then v is the k reactivities or equilibrium association. So the reactivity of a given reaction network that just is based on how you define it. And then just a note, v of y gives the matrix we are looking for when starting or beginning the algorithm or going through it again. Y naught is our initial condition or initial state vector. We will use that to just use y in continuous loops. Then t length is the max length of time. We will build up to this. And so when eventually we hit t length, we will end the algorithm if we don't have a propensity of 0 before then. So I define t starting time at 0. One thing I did here is with ts and our results is that we are saving these. So like every time we get a new time increment, we save the time, we append it to this array, along with appending it to the results so that we can then graph it later. That's the whole idea of that. This is just going to convert our initial state function so that we save it as y so that we can use it down here. And that kind of gave more in-depth explanations, but I think that did pretty well. I guess actually this is a cool point. So I saved it as a list because these are dynamically resizing. We will be randomly choosing our time intervals, right? The whole randomly choose a time of the exponential distribution of 1 over a naught, if you remember, or I guess not a naught, we'll get there, but 1 over the propensity, the total propensity. This small little time increment is going to be appended onto our list TS, and then the the corresponding result will be appended here. So basically it's really dynamic, and so it's going to be slower than, say, pre-allocating these as NumPy arrays. That's what I try and say here, but essentially, yeah. And so here it actually gets to our loop point. So while true, I just kind of define it as while true because we'll be continuously looping. The breaks, right, are going to be based on our time and propensity. So we don't really need to break out of this loop until those happen. But anyway, propensities equals v sub y, right? Our rate function v that gives us the propensities as a function of the current state. That's our propensities. A naught, I kind of gave it away earlier, but this is our total propensity. If A naught is 0, if we have no propensity, we break. Then we want to choose our time increment. So if we follow along here, our time increment. So if our propensity is 0, nope, we continue, i.e. we don't break out. So we're continuing, and we want to draw the time to the next reaction. So randomly picking a time, i.e. our dt, or change in t. And we randomly do this using the random library. In this expo variate method of A naught, which is our total propensity, this is just the same thing as just saying np.random.exponential of 1 over A naught. It's these are, you can use either, they're synonymous. And so this picks our random dt, or random very small dt, the time that it takes for the next reaction to occur. If t plus dt is greater than our simulation length, we want to break out. That's just our second break. So we break out if it is, but if not, we'll continue. And then we want to pick what reaction to do, what random reaction. So we picked a random time, now we need to pick a random reaction. And so I saved this all as IDX, but we're going to use our random choices method with the population, the range of the length of our proportion, or of our propensities. And so this is just indexing these propensities. We'll weight them as the propensities. And so once we rate the propensities and pick one, since we just run it once, right, we only want to pick once because we only want one output. Every time we execute a reaction, the propensities change, right? We want to do with one small time increment, one reaction, because then the states will change and we'll run it through again. Anyway, so this is our random choices method that'll help us in our algorithm. And so we'll get some output, and so we will pull out these columns from the stoichiometry matrix for all the specifics with respect to that reaction. So change to apply, I saved it as, which is just the index applied to the state vector. We need to reshape this because it comes out of 2D array, so NumPy kind of makes it a little funky, but essentially if you just printed this, you'd see that it's a two-dimensional array. You really just want it as a one-dimensional array, so that's what I do here. This just converts this output to a one-dimensional array so we can keep using it. And then we'll add our time, which is our random time increment. We will add our random y, which is our change to apply that I messed with here. And so that changes our state function. And then we will save these times and save our results with each little dt that we do. And so then we loop all the way around, right, because we're still in this while true loop. So we'll keep looping until we break out if the propensities are 0 or if the time exceeds the amount of time that we need or that we define. Our return eventually, once we go through a bunch of times, will be this set of time increments that we randomly chose along our path, and then their corresponding results. And then I convert this all to a NumPy array for ease later, really. So I'm going to go ahead and run this, show you that it actually runs. So I ran this again. These are about the same. Then I'll go ahead and run this. No errors, that's good. And then we'll get into an actual example. So we have our kind of reaction or our algorithm here. Now let's actually get into an example. Very simple. So basically, first I define this v of yc as just c is, I should have put this as k, but this is our kind of our reaction constant that's going to be applied on our initial conditions. This is our state vector, and so our state vector will be a combination of our initial conditions or state vectors with the rate function. Sorry, I meant rate function v, which is dependent on our initial conditions and state vectors, as well as our c in this case, which is just our reaction constants, so i.e. the rates of the reaction and so on. So that's simple. Okay, and so then we got to set our initial conditions for our little example. So I just set n equals, if we would cross-reference this back to n is our stoichiometry matrix that we input. So I just made it -1 and 1. I made our y naught essentially a numpy array of 50 and 0, so a lot of a's, no b's. Our time length will be 10, and our function, you'll see y made a bunch of a's and no b's. It's just because we're mapping a's to b's. And so, yeah, so I define this lambda function. This is where this function comes in. And then we want these accounts, b counts. These are going to basically, essentially what's happening here is like you have a counts, and then after the reaction you'll lose those a's, and then you'll gain a b. And so these will change, our state will change as we go. So I'll go ahead and plot this. And so if I plot this, you'll see that our a's kind of go down pretty fast, and then you know, that's just kind of how it looks. It's a very simple reaction, right? We have a very simple reaction pushing forward with a's just going to b's at our initial condition, and the a's kind of gradually lob off, and b's will gradually join with the loss of a's. So that's pretty much it. I hope to get into an actual more complicated example, so that it's not just a simple A to B reaction sequence. But thanks for watching, and I'll see you next time.